Very well. So since we just started to touch this idea of having a clock, right, in our system, this clock signal that is going to go up and down, and is going to orchestrate everything that is going to happen in our system, right? Again, no surprise that in a computer system, right, a traditional computer system, you're going to tick, tick, tick the clock, and as we just saw, stuff happens, right? We actually store the values inside our flip-flops or inside our latches. We actually send values to the bus. We start fetching values from memory. So everything, all these steps and these stages that change state, tick, change state, tick, change state, right? The clock is what orchestrates everything, right? It's going to be the synchronization device for us. And to be honest, most books, they mention that there is a clock, but they actually don't dive in too deep in what this clock really does or how this behavior of this oscillation up and down, right? This oscillation of 1, 0, 1, 0, how do we generate this? I'm going to be a little bit different, and I want to actually open this parenthesis, and I want to talk about the system clock. How do we actually create this in the first place, or where did this come from, this oscillation, this frequency, right, this rate where things move from low to high at this very consistent, very deterministic frequency, right? So if you think about clocks, right, if you just kind of go back in time, I'm going to skip the whole sand falling on a glass bottle, or even, the sun casting a shadow in a certain position. I don't want to think about those timekeeping devices, right? That is basically just to tell time in a very imprecise manner. I'm thinking about precise or good enough ways of measuring clock and time. I think I'm going to start with one of the most common clocks that, which is the pendulum one, right? I do remember if I went to a friend's house, they had that pendulum clock on their house, right? It was really big, really majestic pendulum clock. And that was one way, right? This idea that we have a pendulum that oscillates at this precise frequency. And I think we can all tell that the rate of that frequency is a function of the length of that pendulum. So the longer the pendulum, the longer the length, the slower is going to be the oscillation, right? The shorter the pendulum, the faster is going to be the oscillation. So it is this inversely proportional function, right? This equation that you have the longer the length, you're going to have a slower frequency, and the shorter the length, the faster frequency. So that was a very common type of clock, but there was a big problem with this pendulum clock, which was people that had to keep time and use these timekeeping devices at sea, right? So if you were in a boat, in a ship, pendulum clocks, they were definitely unreliable, right? For obvious reasons. So what you will see is the rise of this type of clocks that use this spring. So you had this weight that was attached to this curly spring, and then that spring started to vibrate, shrinking and releasing, and that it is actually pretty accurate, the frequency that we get out of that spring. So these clocks, these watches that you see, you have these wrist watches that use that spring still, they do use the system that you have a weight connected to this spring that vibrates, that oscillates at a certain frequency, right? And this system was actually okay for us to actually go and insert in a certain special device, these maritime clocks that keep time at sea, right? So you have almost like this gimbal thing that it doesn't matter how much you go left or right or how much you shake the boat or shake the ship, that thing keeps in balance, and that timekeeping device, the little spring inside, is okay. You keep having that consistent and accurate frequency, right? That rate of change keeps being the same. So you can keep time. And keeping time not just for the sake of keeping time, but also because keeping time was required for the systems to tell the latitude and the longitude of where we were at sea, right? So this motivation, right? The need for keeping time in different places are more reliable alternative to pendulum clocks. But to be completely fair, that is not what we're going to use to keep time in these traditional computer systems. What we use is something a little bit more accurate, a little bit more elegant, which is usually, we're going to use the power of a crystal oscillator. right? So if you think about the way that computers keep time, we usually use these components, we usually use these ideas of having a clock, and most of the time the most popular option is to use a crystal clock. And crystals, they possess some properties that they vibrate at certain rates, very precise rates, and that vibration, right, whenever we go and we fetch and we read that vibration is going to give us this oscillation of charge that we need, right, going from minus to plus, plus to minus, minus to plus. So you have this oscillation going on. All we have to do is just go clamp those values that we get this digital discrete 1, 0, 1, 0, 1, 0. Everything is based on this vibration of this crystal quartz. And if you think about crystal quartz, if you are going to actually purchase a component that has this crystal oscillator, it's going to look something like this, right? You're going to buy a little component that has this metallic protection shell, but what you really want is what is inside this shell, which is this crystal quartz, which is silicon dioxide, which is a really, really abundant element in the crust of the Earth that is going to vibrate and oscillate at a specific rate, giving us this clock power. And most of the time we will be happy with this explanation and move on, but you know us, right? We like to dig a little bit deeper on why things work. So the property that makes this vibration happen, right, is this crystal property that we call piezoelectric effect. So this piezoelectric effect is a property of the molecular structure, right, this atomic unit structure of the silicon dioxide, where, let's just read what it says. When compressed or bent, a piece of quartz will generate a charge of electricity. So if you go and you compress this material, or if you bend, if you apply some mechanical stress into this crystal, it is going to generate a charge of electricity for us. But also, likewise, it goes the other way as well. So if electricity is applied to a piece of quartz, it will bend or change its shape. So you can go from both ways, right? You can either bend and apply some mechanical stress into that material, and that bend, that compression, is going to generate a charge of electricity, is going to result in voltage. Or you can go the other way. You can apply electricity to that crystal, and that charge is going to deform the material, deform the crystal, compress or enlarge depending on what you're doing. And of course, crystal quartz is not the only material and the only crystal that possesses this piezoelectric behavior. So way back in 1880, two French physicists, Jacques Curie and Pierre Curie, two brothers, and yes, Pierre Curie is the husband of Marie Curie, right, the famous researcher that found about radiation and died because of that. So Jacques Curie and Pierre Curie, these two brothers, they demonstrated this phenomenon of certain crystals where you change shape and then they generate this charge, right, this change in electricity. So to summarize what's going on, the piezoelectric effect depends strongly on the material atomic structure and how charge is actually distributed in that atomic structure of the material. So it's all about how charge is distributed among those atoms in this unit cell. We know by now that these crystalline materials, right, the atoms in a crystal material, they are usually arranged in this three-dimensional pattern, right? You have this large grid of this atomic unit. This pattern that I'm talking about, we have this building block, right, which we usually call this unit cell. And this unit cell repeats and repeats and repeats, and we have this large grid with this crystalline material, right? So you have this repetition of this unit cell that go and go and go and then create this fabric, this big grid of this structure, of these unit cells. Right, so if we take an element, a crystal, that is non-piezoelectric, the atoms in this unit cell, they are going to be distributed symmetrically. And this symmetry is why they do not possess this piezoelectric behavior, right? So since the atoms in this structure, in this unit cell, they are symmetrically distributed, there is no imbalance of charge. All these atoms, they are distributed in this unit cell, and they are symmetrically around this central point of charge, right? You can think of it almost like this center of mass that is perfectly balanced in the middle, but in our case, it's the center of charge, right? So this symmetry of this crystal is what makes them non-piezoelectric, all right? But on the other hand, if you have a piezoelectric crystal like silicon dioxide, right, like quartz crystal, this type of material, they have a non-symmetrical atom distribution. And therefore, they do not have this center of symmetry of charge. And this lack of symmetry is what makes them good candidates for having this piezoelectric behavior. So if you look at a quartz, right, which is a piezoelectric material, which is made of silicon and oxygen, right? The oxygen atoms, they have a slightly negative charge, while the silicon atoms have a slightly positive charge. So that difference of charges, it creates this separation of charge, or sometimes what people will call this dipole around each one of the bonds. Right, so everything all right so far? We have silicon atoms and we have oxygen atoms. They are a little bit negative on the oxygen and positive on the silicon, and then we have these dipoles, but usually in a normal state, these dipoles, they cancel each other out, so there is no real net separation of charge across this entire unit cell, right? So in a normal state, if you don't bend, if you don't cause any stress, these dipoles, this difference of charges, they cancel each other out. But if by any chance you go and you squeeze, you compress that material, the atoms are going to shift, and because that structure is asymmetrical, the dipoles are not going to be able to cancel each other out anymore. So this stretched cell is going to end up with a net negative charge in one side and a positive charge in another side. So we're going to have this imbalance of charge in this unit cell. And of course, this imbalance of charge in this unit cell is going to ripple and affect all the other unit cells in this crystal, right? In this big grid of unit cells that you have in this crystal material. And at the end, what you're going to have is this charge imbalance repeating and replicating across the entire material, and you're going to end up with charges collecting on these opposite faces of the crystal. So in one side of the crystal, we're going to have positive, and on the other side of the crystal, we're going to have negative. That results in voltage, right? Going back to the basics of what we learned. If you have this difference of charge in this, one phase has negative imbalance charge and the other phase has positive, this difference between these charges of these two phases are going to end up in voltage. And everything has to do with this lack of symmetry of this unit cell for the silicon dioxide, or also other materials that possess the same behavior. Right? Everything has to do with this lack of symmetry. If you go and you squeeze this material, you're going to have an imbalance of charge. It's almost like you are changing that center of charge right in the middle. It goes a little bit to the one side or a little bit to the other, so you have this difference of charges because of this asymmetry that you have of this material. I just want to point out as well that the stronger the stress that you apply, or the stronger the compression that you apply on a crystal, the larger is going to be the voltage generated, and also the other way around as well. The bigger the electricity that you apply, the more is going to deform and bend that element. Right? So you have this function of the more you compress, the more you stress, the more voltage you get, and the more voltage you apply, the more stress and the more deformation you're going to get into that thing. That is also true. Right? So you kind of go one way or the other. And what I want to just finish with, right now that we kind of understand a little bit this high-level understanding of how we get this oscillation, you're going to see that the most famous symbol in a circuit, right? If you find this symbol right here, they usually represent a crystal oscillator. And you know what? Just before I finish, I just want to show you something quite interesting, which is, do you remember how we spoke about the Paul-Falstad circuit simulator, which was one option that we had to show these diagrams and to create these circuits? If you come here down, there is this Pong circuit level simulation. If you click on this link, this is a simulation of the 1972 Atari game Pong at circuit level. So you know those big arcade machines with Pong? This is a simulation of that 1972 big cabinet, right? The Atari Pong game. And this is super cool. It's such a great learning tool. You start by generating a clock of the system, and then you end up evolving and creating the circuit that goes and draws the net, and then you have a circuit that controls the pedal positioning based on the input joystick controls, and then how you draw the pedals, how you draw the score. So each one of these links is going to take you to a different circuit. What I'm really interested in is the first one, right? We have to, before we do anything, we have to generate a clock signal. And for that, if you look at the clock generator, Look at this one right here. This is the symbol that I just showed you, right? So we're gonna have, let me just stop. We have this circuit right here, which is responsible for using a crystal oscillator component, right? One of those crystals that you can buy. And when you buy this component, is that metal shell where inside what you have is a very small slice of crystal quartz with an electrode that you're going to actually apply electricity, and that little slice of crystal quartz was sliced precisely to give you a certain vibration. So as you apply electricity, it is cut in a precise way that you get a specific vibration out of it, right? A very deterministic, a very precise rate of oscillation, that frequency of oscillation. Cool? So this thing right here is that component, is the crystal oscillator. And then we have a complex circuit right here with resistors, with a capacitor, with some inverters, and then it has an inverter and it has a flip-flop, something called a JK flip-flop, which we're going to look very soon. But the whole point of this circuit right here is using this oscillation from the crystal and controlling the signal, right? You use these resistors to clamp the value, right? So it's not that big. You go and you shrink the values to a precise value that you want. So you use resistance for that. And this right here is the clock signal that we want to go and drive our arcade cabinet, right? So this is what drives the entire game. If we run, you're gonna see that this clock goes on, off, on, off, on, off, on, off, on, off. This is the frequency that I need to go and play my game, right? And you can see right here, this wave variant of this 1, 0, 1, 0. You can actually read the signal as time passes. I just want to point out something before we go. Here the description says that this is the main clock generator of the arcade machine of Pong. It is a 14.318 megahertz crystal oscillator, which is this one right here. And this oscillator drives a JK flip-flop, which halves the frequency of that crystal to generate the actual 7.159 megahertz clock that is actually required for the game. So what you will see right here is this. This crystal is probably generating this frequency, 14.318 megahertz, right? Millions of times per second. That is the rate. This is the frequency, 14.318 millions of times per second. But this is not the speed that the arcade requires for the game. Because if you think about the game and the arcade, you're going to have the arcade, and the arcade is not just the clock. The arcade is all the other components on that cabinet, right? So there are components that are a little bit slower, there are components that are faster. You need a specific frequency here for everything to work together in synchrony, right? So the speed that you actually need in this case for the game, for Pong arcade game to work, is 7.159 megahertz. So what you're going to have to do is you're going to have to shrink this value. You're going to have to go and find a way of having this value in this case. And you're going to see that to have that value, to divide by 2, we are using this JK flip-flop. Look, we're going to learn why this works very soon. We're going to learn about JK flip-flop very, very soon. And I want to come back and then explain why this is responsible for having that value. But all I want us to take from here is the fact that we do have a crystal oscillator. If we start, we're going to see that. Do you see this oscillation going back and forth? We use these resistances here, right? These resistors to go and shrink the value or modify the current to actually get the healthy values that we need, and capacitor as well. So everything that you see here is a circuit to generate this clock, which, as you just saw, is the value of 7.159 millions of times per second. This is the speed required by the entire cabinet, by the entire board to work. Because think of it, right? It would be, if you just want a faster machine, it would be just a matter of getting a faster clock. But that is not really feasible, right? It's not just a matter of going and increasing the speed of the clock to get faster machines and faster computers. The computer is a collection of all the components around this clock. So everything, you have components that are a little bit slower, you have components that take a little bit longer to respond, components that are a little bit faster. You need to find a clock speed that matches all these components together, right? The computer needs to work as a whole. So that is why in this case, in this very simple case, a crystal clock of 14.3 megahertz had to be changed, and this circuit is responsible for halving that value to 7.159 megahertz. All right, so that's it. I just wanted to open this parenthesis, talk about the clock, and now closing this parenthesis, because we're going to have a crystal clock that is going to actually orchestrate and synchronize everything that is happening in our system, right? As we just saw, we're going to have flip-flops that are going to have this common clock signal that we're going to go and store everything, synchronize the storage at this tick of the clock. So that's why I thought it was important for us to open this parenthesis and just speak about the system clock. Great stuff.